Okay, so this is going to be a pretty short video, just to talk about relative velocity. We don't talk about it too much. We'll have a few questions on it that will come up on the tests, one or two, but just want to make sure that you guys understand the concept. So I'm going to be gone on Friday, so don't panic if you guys are struggling with the work on Friday. When I come back on Monday, we will, or I don't know when I see you, Tuesday, we will go over some of this stuff and make sure that you guys are feeling better about it. So let's talk about it. So relative velocity is really about relating the measurements of two different observers. And so it's maybe useful to use a moving frame of reference instead of a stationary one. So it's important to first specify the frame of reference that you're talking about, since the motion might be different depending on what your frame of reference actually is. So really it's like which way, how are you looking at things? There are no specific equations you have to know for this. Really the easiest way to do this is to recognize the pattern of subscripts that we can use when we write them on our variables. And so you're going to assume the following two things. First, that E is an observer, stationary with respect to the Earth. So E basically just stands for Earth. A and B are two moving cars. And we'll just kind of use those references for now. So if we wanted to say the position of car A relative to E, or relative to the Earth, we would say RAE. So it goes position of car A relative to Earth will be written as RAE. So that means that position of car B relative to Earth would be RBE, and position of car A relative to car B would be RAB. And so then we come up with this equation where it says that the position of A relative to B is equal to the position of A relative to the Earth minus the position of B relative to the Earth. And I'll show you what this means. Right now it just sounds a little confusing, but you just want to keep those subscripts in mind. So for the position of car A relative to B in vectors, so here is the position of car A relative to the Earth. So here's Earth at the origin. The position of car B relative to Earth is represented by this vector because the Earth is here. Now the position of car A relative to car B is going to be this vector here because B isn't at where the Earth is, and so its position, the position of car A if you're in car B looks different than if you're standing on the Earth over here. That's all that it means. This slide basically just talks about it being true for velocities as well as for positions. So same kind of thing, but now it's just velocity instead of position. Same kind of equation. So some problem-solving strategies for this, these types of problems are to label all the objects with a descriptive letter. Look for phrases such as velocity of A relative to B. Write the velocity variables with appropriate notation. And if there's something not explicitly noted as being relative to something else, it's probably relative to Earth. So you can just assume that. And then go ahead and take the velocities, put them in the equation, and solve for the unknowns. It's not too crazy hard. So this is just kind of one example. So if we wanted to know the velocity of the boat relative to the river, then we would have to take the velocity of the boat relative to the Earth, the velocity of the river relative to the Earth, right? And then plug those in and basically subtract the velocity of the boat relative to the Earth minus the velocity of the river relative to Earth, and that would give us the velocity of the boat relative to the river. It's a lot of moving around with these variables, but really if you just label them and then you plug them into these equations, it's not that bad. So let's just do one example. So a train is traveling with the speed of 15 meters per second relative to the Earth. So, and then a passenger standing at the rear of the train pitches a baseball with a speed of 15 meters per second relative to the train off the back end in the opposite direction of the motion of the train. Okay, so it said that the train was moving with a velocity of 15 meters per second relative to Earth. So the velocity of the train relative to Earth, and I'm just made it to the right, so I'm going to make mine positive. Then it said that there was a little person, I guess, on the back of the train, and they pitched a baseball in the opposite direction for the motion of the train, but at the same speed of 15 meters per second. So the velocity of the baseball relative to the train, they said, was 15 meters per second in the opposite direction. So we're going to need a negative sign there. Okay, so Our goal is to figure out, in part A, it says to figure out the velocity of the ball relative to Earth. So someone's standing outside of the train, watching as it goes by. You pretend like you can see the guy throw the ball. What speed would we see the ball moving? So we want the velocity of the ball relative to the Earth. Now, if you remember our form for our equation, we would write the velocity of the ball relative to the train equals the velocity of the ball relative to the Earth minus the velocity of the train relative to the Earth. So that's all we're going to do, is we're just going to plug the numbers in. So the math is really, really easy. It's just the setup. But if you follow this kind of pattern, right? So like if you notice, like I just remember like the ball goes first, so ball goes first here, train goes second here, so train goes second here. The Earth ones are on this side, and then the combination of the two that doesn't involve the Earth are on the other side. And so if we just plug in our numbers, we have negative 15, we have the thing that we want, and then we have positive 15. And so if you do the math and you add the 15 to the other side, you get that the velocity of the ball relative to the Earth is actually 0 meters per second. Which should make sense, right? Because originally the ball was on the train going 15 meters per second to the right. Relative to the train, the ball is now being thrown 15 meters per second to the left. But if we're a bystander outside the train, we see the train and the ball moving to the right at 15. The ball is thrown backward at negative 15. And so the 15 and the negative 15 just cancel out, and it looks like the ball is not moving at all while it's being pitched. And so our velocity is 0 meters per second. I know it's a little bit weird to think about, but we'll do some demos when I come back, and I'll show you how this works. So let's do part B. So that was part A. So part B says, now same question, what's the velocity of the ball relative to the Earth, if now the ball is thrown in the opposite direction. So now the ball is thrown to the right. So the velocity of the train doesn't change. We still have 15. But the velocity of the ball relative to the train is now positive 15 because it's being thrown to the right. So now, as an observer outside the train, let's find out what we would see. So same equation. We're just going to use the same VBT equals VBE minus VTE. We plug in. We have 15 equals VBE minus 15. And then if we add the 15 to the other side, now we have 30 meters per second is the velocity of the ball relative to the Earth. And that makes sense because the train is moving to the right. Get the wheels. The train is moving to the right 15, and then also, so the ball has that 15 because it's moving to the right, but then it also has its 15 that the guy threw for the velocity of the ball. So now we have the 15 of the train plus the 15 of the ball, and so the total on the outside, if you were standing outside looking at the ball, it would look to you like the ball were moving at 30 meters per second. You may not be able to tell the difference standing outside the train, but mathematically that's how it comes out. So there are going to be some more difficult ones with vectors and things like that, but really if you just use this equation, right, and you can subtract vectors or you can add vectors if you add this one to the other side, right, so this equation really becomes VBT plus VTE equals VBE. That might be useful as well in terms of vectors because you can just add two vectors together. Remember to add them with components and things like that. So this way it works as well, and I kind of like it because then like the middle t's kind of cancel and you just get VBE, and you see how that kind of turns into VBE. Like I said, we'll practice this when I get back, and it's not a huge part of your test, but you do need to kind of know how to do it. So we'll practice and it'll be on the review. So do your best on Friday when I'm not there, and then we'll come back together on Tuesday when I see you and make sure that you guys are feeling good about this.